specifically about Navier-Stokes problem, which is solving Navier-Stokes equations in the whole space. As a byproduct, I have a solution of the millennium problem about the Navier-Stokes equations. I will start describing the problem in a moment, but first, this is my email address to which you can send questions. Also, you will have some time to ask questions after my talk. Now, the goal of my talk is to show that the Navier-Stokes problem doesn't have a solution, and the solution to the Navier-Stokes problem, if you assume that the initial data are not identically zero, can be proved that these data are indeed equal to zero. I will give you a detailed proof of this, but this paradox, which I call the Navier-Stokes problem paradox, shows that the Navier-Stokes equations are not a correct description of the fluid mechanical problem for viscous incompressible fluid. So it calls for the physical investigation of what is a correct description of the fluid mechanics. Now, the millennium problem that I mentioned is a mathematical problem, and the problem consists of finding whether the solution to the Navier-Stokes equations exist for all times, and if this solution is bounded. That I will discuss also a little, but from the Navier-Stokes problem paradox, it follows that the millennium problem about Navier-Stokes equations is not solvable. Now, people who contributed to the Navier-Stokes equations are Claude Louis Navier and George Gabriel Stokes. Navier equations were written in 1822. It's about 70 years after Euler's equations. And Stokes didn't know about Navier work, and he continued to work on independently on Navier-Stokes equations from about 1840 to 1850 maybe, and that is the reason for the name Navier-Stokes equations. Now, the Navier-Stokes problem I will be discussing consists of solving these equations. This is Navier-Stokes equations. F here is an exterior force. P is the pressure. U is the velocity vector. Nu here is a positive constant viscosity. U naught is the initial data. This equation is also quite important. Divergence of U is 0. Now, I will use the following notations. This will be the scalar product in L2. The norm in this space is given by this formula. Integral will be taken over R3. The initial data will satisfy the divergence zero equation. The Fourier transform is denoted by this formula. Well known, the Parseval identity. And there are two formulas, this one and this one, that I will use several times later. Now, by W, I denote the Banach space of these functions. H1 will be the Sobolev space, and C will be the standard space of continuous functions with subnorm. R plus is the positive semi-axis of the t-axis, time axis. Now, I assume throughout this inequality on the data, this is initial data, this is exterior force. These are weak assumptions, but they can be more weakened, which is not important. Now, the first basic result is an a priori estimate, which is written here. By C, I denote various constants, positive constants, not depending on T or N or X. Now, these notations may be mentioned. By this, I denote the derivative of uja. Uj is a vector field, and uja are projections of this vector field. This basic equation can be written in these notations like this. Now, first result is easier a priori estimate, which says this. And equivalent form via the identity I showed you is this, with the Fourier transform. How do I prove this a priori estimate? I multiply the original equation, this equation, by uj, and then integrate by parts. Now, I use the following identities. This, by integration by parts, is non-positive. The basic identity is this. So, as a result, I get this inequality. And if I integrate it, I get this inequality. By my assumption, this is not more than a constant. That's the sketch of the proof of first basic a priori estimate. I note that from this a priori estimate, it follows that if the data are zeros, then the u, the velocity field, is zero. But my goal is to prove that the Navier-Stokes paradox, Navier-Stokes problem is contradictory. Physically and mathematically, it is not correct. That's very recent and novel statement. Please consider it and my arguments in detail. You will have a presentation file from the organizers. Also, there will be references. I have a book on this topic published in 2021. Now, secondly, it follows that the Navier-Stokes problem doesn't have a solution defined on all of the semi-axis of time. From this, one concludes that the millennium problem about the Navier-Stokes equations is solved, and solved negatively somehow. Now, first I prove this basic a priori estimate. What are my proof? What are my steps in the proof? First, I obtain integral equations equivalent to the Navier-Stokes problem. Such equations one can find in the literature, in the work of, for example, Toshio Kato. But I use the Fourier transform of these integral equations. And the Fourier transform equations were not used earlier. Then I derive integral inequality of this type. B here is related to the solution as shown here. B naught is the initial data. You see that the basic feature of this integral equation is that the kernel here is hypersingular, and this integral diverges in the classical sense. So part of my presentation is to define, to give a new definition of this hypersingular integrals and prescribe a definite sense to these integrals. With this inequality, I relate an integral equation of this type, also hypersingular, and I will solve this equation analytically, explicitly. I will sketch a theory that I have developed for these integral equations and inequalities. I will prove this inequality, and from this inequality I derive the Navier-Stokes problem paradox. This is my plan. Now, if I prove that this inequality holds, then theorem A is proved, because if this is true, then this follows by Parseval inequality, by Parseval identity, and I have already proved this inequality, so the desired a priori estimate is proved. On the Navier-Stokes equations, there are very large literature, several books, and probably thousands of papers. Since I do not use actually the literature, I will mention only one book by Olga Ladyshinskaya, and will not refer to any other sources. Now, the integral equation that I derive first for Navier-Stokes problem is this equation 7. Here, G capital is some Green's function, which I showed you explicitly later, and F here is the data which is given explicitly here. G capital is the known Green's function, which I showed you, which I will show you later. Now, the equivalence of the Navier-Stokes problem and integral equation 7, one can prove by applying this operator to both sides of equation 7. The result is written here, and it's, if you take this term to the left and this term to the right, will give you the Navier-Stokes equations. The Green's function G capital is defined by this formula explicitly. It satisfies this equation, the zero initial data. PM here is given by this formula. That's a tensor. Delta is the delta function. From this formula, it follows this estimate, which I will use several times. Now, G small is this known function. If I take the Fourier transform of equation 7, I will get this integral equation. Here, star denotes the convolution in R3. Equation 8 is equivalent to the Navier-Stokes problem because it's equivalent to integral equation 7 via Fourier transform, and integral equation 7 is equivalent to the Navier-Stokes problem. So these are formulas that are useful in what follows. Now, first, from the Cauchy inequality, I have this relation. That's trivial. From this inequality and the integral equation 8 that I showed you, this integral equation, I derive this integral inequality. B here is defined by this quantity. Norm, I recall, is the L2 norm in the whole three-dimensional space. And this B naught, I will show you, I showed you earlier, it's this initial data. In this equation, the kernel is hypersingular. So this integral diverges in classically, and I will define it in a new way later. Now, from equation that I showed you, from equation 8, this inequality follows by taking absolute value. And since I already proved that norm of U tilde is bounded, I will get this inequality. Now multiply this by absolute value of xi and take L2 norm. Use this relation, which is easy to prove, and you get this inequality. The integral equation corresponding to this inequality is this integral equation. Now, the basic result that I will establish is this inequality. Now, I am passing to the definition of the integral equations with hypersingular kernels that I derived earlier. Let L be the Laplace transform, which is defined as usual by this formula. By phi lambda, I denote this function. Gamma here is the gamma function. For t less than 0, this function t to the power of lambda is 0 by definition. The convolution, one-dimensional convolution, is defined by this integral. I can rewrite in these notations the integral inequality 8 that I have this integral inequality, and here 13, as follows. And C1 here is the absolute value of gamma function of -1/4. This gamma function is negative. I take absolute value. It's a fixed positive constant that I denote by C1. The integral equation corresponding to this inequality is this, with the same C1. Now, for a real part of lambda, the Laplace transform of this convolution is given classically by this formula. P here is the parameter of the Laplace transform. Now, I will prove that for all complex lambda, and real part of P positive, as always, is in the Laplace transform. The Laplace transform of phi lambda is given by this formula. Classically, this formula is known only for lambda positive, real lambda positive. If this formula is established, I can write the solution to the integral equation that I have explicitly. And I can define this convolution for lambda equal to -1/4. That gives me the kernel 5, this hypersingular kernel. By this formula, it's inverse Laplace transform of this function of P. I will also prove that this function of P is indeed a Laplace transform of some function, actually even bounded on the semi-axis, as I will prove. Now, the definition of derivation of this formula is given in the following way. If I introduce the new variable pt is equal, say, to tau, I will reduce it to the gamma function integral, and I obtain this formula. Now, I will okay. I will solve this integral equation using the sketch that I explained by taking the Laplace transform of this equation, obtaining this formula, solving for Laplace transform of Q, and getting this explicit relation for the Laplace transform of Q. The solution Q is given by the inverse Laplace transform of this formula. Now, if B naught is smooth and decays fast as t goes to infinity, then I will have this type of inequality for large P. I will check that this function is analytic and bounded in the region real part of P positive. And obviously it is this order of magnitude for large absolute value of P, real part of P positive. So my theorem B says that if B naught is smooth and rapidly decaying when t goes to infinity, and L of Q is satisfying this inequality for large absolute value of P, real part of P positive, and beta greater than 1, then not only equation 16 this integral equation is uniquely solvable, but also its solution is in this space, so it's continuous and bounded uniformly with respect to t on the semi-axis, and Q naught is 0. This is a key new point. The conclusion of theorem 1 well, here it should be not theorem 1, but theorem B, this theorem. The conclusion of this theorem follows from lemma 1. This is lemma 1. This is purely analytical lemma. The lemma says that if the function f capital of P is analytic in a real part of P positive, satisfies this inequality for large absolute value of P, everything takes place in a real part of P positive. And P is this, and f of is belongs to L1 locally, and beta is greater than 1, then f of p is the Laplace transform of a uniformly bounded function whose value at 0 is 0. Let me sketch the proof of this lemma. Actually, it will be a quite detailed proof. I defined f of t by this formula. I assume that for simplicity only, that sigma is 0 here. Now this integral converges because beta greater than 1, so f is in this space not only locally but globally. By this reason, f of t is a continuous function, and its supremum for t positive is bounded. So the main point is to prove that f at 0 is 0. Now, f at 0 is given by this formula. I denote the right-hand side for brevity by I. The integral, as I mentioned, makes sense because f is in L1 on this axis. So, by analyticity of f, for any n, I can write that this I is a limit of this integral over a closed contour. One part of the contour is along imaginary axis from -n to n, and the other is the closure of this interval by a circle of radius n on the right. Now, since by my assumption f decays for large absolute value of p faster than 1 over p to the power of 1 over absolute value of p to the power of beta, the integral of this in the limit will give 0. And since integral of the closed contour of an analytic function is equal to 0, I will get that the limit of this first integral, which is this integral, is equal to 0. But this means that f at 0 is 0. And so lemma 1 is proved. Now, I have assumed in the beginning that the initial data are not equal to 0, and I proved that this quantity is 0, therefore this quantity is 0, and then the support of this Fourier transform is 0, and since u at x0 is not a distribution, it's equal to 0. Therefore, the Navier-Stokes paradox is proved. The Navier-Stokes paradox again is this: assume that u at initial time is not identically 0, And if B naught is smooth and rapidly decaying for large T, then the initial data is actually must be equal to 0. Now, I proved the above using this key inequality. If Q at 0 is 0, then B at 0 is 0, and my previous argument holds. To prove this inequality, I need two lemmas. First lemma, consider this operator with A greater than -1. So this is the convolution that can be treated classically. In the space C0 T capital, T capital is arbitrary large positive number. I claim that this operator has spectral radius equal to 0, and this implies that the integral equation of this type with any G in this space is uniquely solvable in X, in this space, by iterations. And the solution can be written by this series, which converges in this space, X capital. Now the proof goes as follows. The spectral radius is defined by this formula. I derive by induction this inequality. And from this asymptotics of the gamma function, it follows that the spectral radius of A is 0. Then all other statements are simple consequences of this. Lemma 2 is proved. Now I need lemma 3. Lemma 3 consists of two formulas, 27 and 28. Delta here is the delta function. Now, to prove the first formula, I take the Laplace transform of this convolution, and by what I proved earlier, it's a product of these functions, and therefore it is this. And since the inverse Laplace transform of 1 over p to the power of lambda is phi of lambda, the formula follows. And this formula I proved earlier. Now, if lambda plus mu is 0, then this relation is obvious and this relation is known. So formula 28 follows. Lemma 3 is proved. Now I am proving this inequality. I start with this inequality, C2, excuse me, I start with this inequality. I apply to both sides the operator phi with index plus 1 over 4 and take a convolution. Using lemma 3, I will get excuse me. Using lemma 3, this formula, I will get this inequality. Now, since here lambda is positive, the convolution preserves the plus sign. And by lemma 2, I can derive by iterations this formula. C2 here is this positive constant. Similar argument for the integral equation gives this formula. Now it is clear, compare formula 30 and 31, that B is not more than Q, which I wanted to prove. So, since Q at 0 I have already proved is equal to 0, it follows that B at 0 is 0. Therefore, U at x equal to 0 is 0, while I assume that U at x0 is not equal to 0. The NSP paradox is proved. Now I can derive alternatively. I already mentioned the uniqueness result that follows from the a priori estimate from theorem A. I derived an alternative uniqueness theorem. It's the same uniqueness theorem, but the proof is alternative. I start with this integral equation. I assume that there are two solutions in the space W, and then I derived that these two solutions must be equal. Let Z be the distance, the difference between these solutions. Then Z satisfies this relation using this inequality that I will show, that I have shown you already. I derive this relation and taking the norm, I derive this inequality where eta is this quantity. Now, if I multiply this inequality by absolute value of xi and take the L2 norm, then I will get this inequality. And taking the Laplace transform of this, and then adding both, I will get this inequality. Now, this inequality I will write in this form. Now, if the Laplace transform of eta is not identically 0, then I will get a contradiction. Indeed, take p to plus infinity. Then it's clear that this term will go to 0. This term will go to infinity. If L of eta is not 0, it's a positive quantity, since eta is positive. I can cancel L of eta and get this inequality. If p goes to plus infinity, I will get a contradiction. 1 is not more than minus infinity. This contradiction proves that L of eta is 0, And therefore, by injectivity of the Laplace transform, eta is 0. So if eta is 0, then this quantity is 0, and therefore Z is 0. The uniqueness theorem is proved. Now, the results I presented are the short presentation of the contents of this monograph. The Navier-Stokes paradox is briefly presented in this paper. In this open access paper, a short presentation of the basic idea concerning solving the hypersingular integral equations and applications to the Navier-Stokes problem is presented. And here, these ideas are presented in a slightly more detail. Now, I thank you for your attention, and I have about at least 10 minutes for your questions. Please ask questions, and if
Thank you very much, sir.
if you, just a second, let me show the file in again.
Yes, please.
Where is, here is my file. Please allow me to show my file again.
Yes, sir. Yes, please.
Yeah, okay. You can use this email also to send me all questions which will be not asked right now. Right now, your questions, any questions are very welcome. Thank you again.